Next up today, we're going to take a brief detour from our machine creativity theme, and we're going to dive deep into reinforcement learning with Chris Poulin. Chris, for the past 20 years, has been specialized in predictive analytics and scalable machine learning in industry, government, and academia, having advised in industry and in government at the very highest level. Poulin is also currently the acting CTO of True AGI, which is one of our sponsors for today, and a spin-off of SingularityNET. And he's an advisor at Singularity DAO, which is a DeFi platform, trading platform. Chris, brilliant to have you here today. Thank you so much.
My pleasure. Okay, we'll wait for the slides to come up. Okay, well, there is sort of an intro that I wanted to do in terms of contextualizing this talk. So if you heard Josh's talk and then you heard Ben's talk from earlier this morning, you recognize that that AGI is an aspirational thing, right? And machine learning is essentially a tool set that's getting us there, right? So the context of this talk is democratizing machine learning tools that get us closer, but not necessarily, promising anything that is particularly AGI. Okay, so that's the first disclaimer. But democratizing tools is very important because the large corporations are clearly building AGI aspiring systems. They are building machine learning systems that directly affect your life. And in case you are suspicious of that statement, just look at the ad tech, at the ads that are being served to you. The machine learning workflows are cognitively modeling what you like, your preferences, and things that you want to do all the time. So understanding that technology, having better access to that technology is an important endeavor. And so my talk today is going to be an open source project called DRL Learner, or Dr. Learner, however you want to call it. And this project is open code, where we are proving human level at tasks, not AGI, but human level at tasks. This technology is prevalent in the research labs like DeepMind and a variety of other labs, but it's not necessarily in the hands of the average user, the average developer, people like yourself. So that's the context of this talk, is that we really want to democratize access to the best of breed machine learning. And then from there, we can get closer to AGI. Okay, so why would you care about reinforcement learning, or why would you care about these types of problems? Well, as I said, obviously the largest corporations are doing ad tech, and they're doing a variety of applications thereof. But generally speaking, we can call these problems time series problems. Time series problems are, there's a variety of data points in time. We're looking at those data points in time, and we're trying to optimize either understanding that time series, understanding the next best action to take in a time series. So we're saying, okay, well, this is the sort of causality of the actual time series as it progresses, right? In the case of earthquakes, which was the sort of oldest slide I could find to show the generality of this. In the case of earthquakes, you're basically saying, okay, well, what's the magnitude of the next quake? So you're trying to predict based on the last data that you've got, right? So pretty straightforward stuff. Obviously, we're starting basic. With the advent of reinforcement learning, it was found, I think, in the 70s, or Ben, when was Sutton? With the 80s. Right. So for anybody that couldn't hear, Ben was talking about right in the 70s. Right. So it's been around for a while. You understand that if there's a reward in a time series, so in other words, if I get a positive reward for tracking a time series, then I can train a system essentially on the front of a neural network or any other sort of representation that it will optimize for a correction based on that time series. So that leads us to a more complex analysis of reinforcement learning, which is temporal difference learning, which is to say that you focus really on a richer understanding of the time series and specifically the diffs in the time series or the differences in the time series. So why would you care about this? Well, it turns out that this has been very industrially useful for Ben and myself over the years. We've done stock prediction. We've done tracking of healthcare and medical records. We've done all sorts of things in this paradigm. So this is a very useful sort of introduction and way to get into this. Okay, so then you may have heard that in 2014, DeepMind came out with a breakthrough. It was very high profile. And that particular breakthrough was to say, okay, if a time series of game images or game navigation is occurring, can we get to a point where there's sort of a reinforcement learning enabled environment where the bot can play as well as a human? Now, why this was particularly chosen as a metric was because games gave you sort of a time series or a temporal environment that an agent would navigate through and try to maximize reward. In this particular case, the reward is points, right? It's actually saying that the game gives you the actual reward and you're ascribing that to the reinforcement learning mechanism for the bot. Now, this was a very high profile result. The disclaimers on this particular implementation is that why it was famous was because they got to human level on a variety of game tasks and game playing, but there were definitely still some areas where the human was beating beating the bot, as it were. And so there were some games that were complex environments where the human was still, the top playing human on a comparison was better. So that leads us to 2020. 2020, a new system called Agent 57 came out, and in that particular innovation was by our friend Adria at DeepMind, and his particular implementation was based on adding a curiosity module to the prior work. There's more optimizations than that. I'm sort of giving an overview today. My colleagues are going to go into much more of a deep dive on some of the implementation nitty-gritty tomorrow. But at a high level, by adding curiosity and replay buffers, which is basically episodic memory, to the prior work, you ended up with human level across all games, and in some cases, you ended up with nearly perfect performance in a variety of games. Specifically, which games are we talking about? We're saying that in games that were relatively complex, better than human performance, and at least human performance in the most complex games that were available in the training harness. So, okay, so that's all sort of high level talk. What does this actually look like? Haley, you can cue the first video, please. Well, that's the next slide. Okay, so we're not going to do a deep dive on each of these video games. That's not the point. The point is that this is what we would call a medium complexity game. The agent has to navigate through the environment and react. You can see that the dimensional space is not very large. It basically has to move back and forth. Why this is a medium game versus some sort of simplistic Space Invaders is that there is a little bit of a change in the enemy bots coming at you, and there's a little bit of strategy involved in this game, but essentially, this game right here is where the prior bot DQN was about at human performance. And that was sort of the state of the art, was that humans were essentially as good as AI agents. But you can see that Agent 57 is actually sort of at least better than the average player, better than I would just picking it up. Next video, please. Okay, so we have the 80s classic Pitfall, and this is where, again, the state of the art a few years ago was that the agents could not actually figure out how to play the game, because you sort of, in Pitfall, those of you that have played it know that you sort of run back and forth with levels, and so you sort of have to remember what's going on in the game space, and then you have to be able to sort of explore around the environment. So in fact, by adding the curiosity module, now the system has reached human level or better in terms of gameplay. So again, you got to think, okay, cool, these games are it's all interesting that the game agent is able to play so well, but the point is that these are very complex games. We're going to show you another one. Next video, please. Okay, so finally, you have Montezuma's Revenge. Clearly, the bot didn't do well there, but the point is that now you get into a complex game where you have to do item management, you have to move around an environment, you have to do strategy, and so it starts to get more into an adventure game, more of a challenging problem, if you will. And so Montezuma's Revenge is a tough game, and it is also a game that almost no agent outside of DeepMind was able to play at a human level of mastery. But again, this Agent 57 environment was able to get to that level. I guess we can go back to the normal slides now.
I think we lost audio from the room.
On how to do an implementation that was similar. Wanted to open source this capability for the community. And so this is actually the literature review. Suffice to say that the key point from this slide is that we decided on a framework called ACME, which is a DeepMind framework, and we built on top of that. So Never Give Up is the specific paper that is the implementation of the curiosity module, and we were able to re-implement that. My colleague Phil Tabor will actually go into the details of implementing curiosity tomorrow on Monday, tomorrow on the first of the two presentations. The key thing is that with Never Give Up, it is utilizing the episodic memory, and it is essentially to sort of overly simplify, when you're getting into a challenging position in the game board, the system stops and then starts trading off and saying, okay, I'm getting diminishing rewards and I'm going to start exploring my environment. And that is the sort of curiosity module. The Never Give Up part is I'm not going to give up in the game. I'm going to just transfer my focus to allocating resources to exploration versus actual, just greedily taking in points. Quick implementation detail for any of you who do this sort of thing. We did the first implementation in TensorFlow. FYI with TensorFlow, it's very good, but in terms of doing multi-parallelism and deploying it in the cloud, we ended up porting it to something called the JAX framework. Initial testing, we did analysis on, again, more simplistic games, then moderate games, and then finally hard games. We built a tensor board. For those of you that are TensorFlow savvy, you can check the statistics and you can watch in real time how the system progresses. This was actually an interesting discovery that there was, it turns out that there's an equilibrium that you need to hit in terms of exploring versus sort of exploiting. And exploration, which is basically the intrinsic motivation versus the extrinsic motivation of the points that you're getting. And you basically have to trade off those two things, as I said, but it turns out that there's an equilibrium state that you have to hit between the two optimizations. Yeah, this is just a test that we'll talk about more tomorrow. This is another interesting slide in terms of how we did meta learning on top of this, which is to say that how do you generate that equilibrium state? How do you do meta learning or learning about learning to then say, okay, if we're going to explore a policy that is an exploration policy versus a points gaining policy, or again, intrinsic reward versus extrinsic reward, how do you actually model that out? So we did what's known as a multi-arm bandit approach, where you're actually doing a prediction of what the reward is going to be versus, so there's sort of an abstraction layer on top of the system. As I mentioned with the JAX slide earlier, we were able to create a fully distributed version on Google GCP. So Acme does not have a lot of support for fully distributed, but we did build that in. We did do validation. I'm not going to show you the videos again because you've sort of seen it once. We validated across multiple games, most importantly in the buckets of easy games and getting over human performance, medium games over human performance, and at least human performance in Montezuma's Revenge, if not better. So in the hardest of games, we were able to duplicate the results. Certainly not on our own. We definitely have to thank the DeepMind guys for giving us lots of feedback along the way. And then the last point was that there's out of modality testing, which is important, as I said, industrially to go into non-game environments. How do you actually enter multiple data types into the system? How do you repurpose the system for other things, not just the sort of Atari games that I told you? So we did some preliminary modality, out of modality testing. So the announcement today is that that code is freely available to you under an Apache license. DeepMind doesn't have a problem with that, and it's very much a open source thing for everybody to engage in. Again, I reemphasize that if we're democratizing things, these types of tools have to get in people's hands, not just large corporations. Okay, so I'll wrap up with lessons learned, and then we can go to Q&A. Okay, so lessons learned. If you're going to deploy this, know that it is pretty expensive due to the fact that this is not AGI. This is, again, a narrow machine learning context, and specifically reinforcement learning is known as a very greedy and not very efficient learner. You're looking at tons of cycles in terms of computing through things. So, for instance, I'll give you an exact dollar cost amount. Montezuma's Revenge, that test cost us $10,000 of compute time. So, I mean, it was just like one game validation was $10,000 worth of compute time. So FYI, if you're going to duplicate this, it could theoretically be hundreds of thousands of dollars if you want to have a perfect run. Noise reduction. So say you ended up doing a 3D environment. Say you started pushing this in a robotics context or into some sort of higher, richer environment than a Montezuma's Revenge, right? In that particular case, your dimensionality, your features grows to this huge level. And in that particular case, your data is going to be just exhaustive. and we calculated some, if we were going to do like an Unreal or some other sort of 3D navigation environment that just out of the box, it would be hundreds of thousands of dollars in compute time just for the simulation. And so therefore, dimensionality reduction and things like contrastive learning on the front end would be a good idea going forward for us. The refocus on representations in AGI, it's actually great to go to later in the day in the context of the earlier discussions, because clearly this is not one of the things I'm excited about is this is a software engineering accomplishment, but there's not a lot there in terms of, it's a neural network that's being trained by the reinforcement learning in a variety of complex hacks. So there's a lot of cool software engineering that went into this, but the point is that optimizing a true representation, whether it's a hypervector representation for data, or some sort of backend system that's better than just a LSTM environment, is definitely the way to go. And then we do have some continuous environment capabilities that are going to come out in the next version. So we will have the ability to support robotics for those of you that do robotics modeling, Majoko, and other sort of simulation environments. We also, as I mentioned, will do API modifications so that you can put in financial data, you can put in any other time series data that I mentioned, and you don't actually have to do just games. And finally, I think that I'm proud of the fact that we have a validated, tested code to share with you guys, but we could always do better at making the community understand what we've done. And so we're going to work on some educational aspects. So you're welcome to join us anytime. And thanks a lot. The team is mostly Ukrainian. Some of them have lost their homes. So I definitely appreciated the fact that they were really dedicated to this project, and it made it extra special.
Thank you, Chris. Very impressive work. Do we have any questions for Chris in the audience? Mike. Thank you, Sarah.
Thanks. Very good. Very good. Two questions. One on the intrinsic reward. First question was on the intrinsic reward. And you said that you implemented curiosity, but you also had an intrinsic reward for one of your games, whereas you didn't take the reward signal from the environment. You did a prediction of the reward signal as a method of intrinsic reward. And the second question was about your using the cloud versus using like dedicated hardware. How much compute processing and memory did you have in the cloud, and how much processing and memory would it have required if you had just gotten a few boxes or something, a few computers?
Yeah. So to be clear, I may have breezed through that too quickly. I'm just trying to give an overview today. But so the intrinsic reward is the curiosity module. That's the default behavior for the agent is it wants to explore, and that's the never give up aspect of it. The extrinsic reward is sort of the standard deep reinforcement learning implementation of I've got this many points as a positive stimulus. So it's really the trade-off between the two that is the intrinsic versus extrinsic component. And in terms of hardware, it's pretty beefy hardware. It's like the highest end Tesla instances on GCP, and without a doubt, I mean, if you have access to a large on-prem GCP environment, GPU environment, then that's a way to go. One of the limitations of the current implementation is that we use Vertex AI, which is a service in GCP to enable scheduling across the nodes. So we will get rid of that very quickly in the next version. Next version will basically be a little easier to use. It will get rid of the GCP dependent components, and it will be also continuous variables and robotics capable.
I'm just trying to get a perspective on the difficulty of the problem you're solving. So if you're in one of these Atari games, how many parameters are you tracking in this time series to, do the prediction? I also don't know if Atari is really a random generator or if it's predictable in some manner.
Right, so you're looking at thousands of parameters or thousands of features coming in terms of the and theoretically millions of permutations of those parameters. And that's one of the reasons why it's so exhaustive, is that it's looking for all these possible combinations without, very naively. And it's not it's not an AGI, and it's not necessarily it's not doing what OpenCog's doing in terms of having some priors of the world that it's navigating. So that gets to your second point of your question, which is, how predictable is the structure of it? Across the 57 games, not very much. This naive implementation didn't afford itself to transfer learning very well. We did some simulations to try to see, could you train it on one game versus another, and then put it on, the third game and see if that worked. And it didn't work too well in this environment. At some point, transfer learning is a very exciting field, and there's all sorts of algorithms in that space. And Ben and I have played in that in the past extensively. And this environment was just much more reflexive, much more, transactional, if you will.
Yeah. Hey, Chris. I was wondering whether you have any plans to use this in more of a multi-agent environment, where there's more cooperative games or competitive, etc.
Yeah, so yes, and in fact, as I mentioned, there's more talks on this tomorrow. We'll get down the rabbit hole of various aspects of it, also including implementation, right? So we'll get really into the nitty-gritty of that. And one of the things that Phil will talk about is the multi-agent possibilities. But in the ALE, which is the Atari arcade and learning environment, it's old school gaming, right? It's old school time series. So there's no actual communication or anything along those lines. So you would have to sort of silo it and make independent agents that competed. But as my colleague Davinko will talk about tomorrow, we already have that in the system. You have, I think, at any given time, going back to the original one of the original questions, you have 128 agents competing at any given time when we're doing training simultaneously. So it really comes down to, like, are the agents competing? Do they know of each other's existence? Those sorts of things. Then the answer is no. If you're talking about multiple agents competing in a large training environment, then yes.
Fabulous, thank you. Ben, did you want to say something?
Quick comment and a question as well. So one thing that's interesting to me in the recent improvements that have caused deep reinforcement to do better and better at games, it's something I've seen in other areas, such as work on machine learning for automated theorem proving in the last couple of years, is what's being done to improve the original version of deep reinforcement algorithms. It's hybridization with other structures that are drawn from cognitive science in a way, right? So I'm in curiosity, like intrinsic reward, and then various sorts of working memory, episodic memory, and so forth. So it seems like you can look at a couple approaches to AGI in this light. Like there's an OpenCog or NARS type approach where you're taking a big ambitious cognitive architecture, which has a component for each part of the human mind that cognitive science has identified, and sort of put something in each box of a human-like cognitive architecture, try to get the whole system to work. Or you start with a system that does one particular thing, sort of emulating one little aspect of what the human brain mind does. Then you glom on more and more modules corresponding to more of the parts of the sort of human cognitive architecture diagram that were left out, right? And one could see both ways of extending this work, right? You could sort of add more and more types of memory, add, say, a symbolic knowledge graph of knowledge about the game, which is used by the deep network. Or you could try to play these games using an open cog or NARS, like leveraging a deep reinforcement learner as one component and something that has other big components in it, right? And I'm sort of wondering, how do you look at the promise of those two approaches? Do you think they will both be taken? And how do you look at the suitability of the code in a concrete sense for being incorporated in both of those approaches?
Yeah, I mean, I think that's similar to how I look at it in terms of, I don't think that there's one best way to go about it. I would say that you summarized it well, that clearly with the way that DeepMind is going about their internal research, they're doing implementations like this. And then they're, to Ben's point, they're sort of incrementally adding functionality to the system. And that's their approach, right? Is a brute force approach where then they're adding, incrementally or bottom up in engineering. That's how they're going. But clearly the other way that Ben's talking is to potentially have the system front end an open cog or a future AI or something along those lines. Any sort of AI platform that has more going on than just a neural network, a simple neural network, and have this be a training harness for that. So I can see either potentiality being very viable.